If we are truly on the cusp of superintelligence, humanity is nowhere near prepared. A warning detailed in a technical report titled AI 2027. It predicts with high probability that humanity loses control over artificial intelligence within the next decade. In this documentary series, I've been developing a mathematical and philosophical analysis for why this will never happen. But our aims have shifted into also understanding how we could build truly intelligent systems, building off decades of research and experimentation. So in the first 2 episodes, we've discussed the foundations of AI research and why they failed. Today is the day we finally do an analysis on AI's first success.
I think that at the moment the time is right to try to make a kind of interconnection between parts of computer science and parts of neurobiology, and I think that the subject which helps you most in trying to make that interconnection are some of the insights one has from parts of condensed matter and statistical physics.
1982. John Hopfield revolutionizes the field of artificial intelligence with one question. Is the stability of memory an emergent property? In other words, does memory simply emerge from complexity? I do a full analysis of complexity theory in episode 2 of this series, which will be linked somewhere here or also in the bio. But to summarize, he's basically talking about this phenomena that we find in nature, where sometimes macroscopic phenomena emerges from complex microscopic interactions. But these macroscopic phenomena, they don't emerge from the microscopic properties themselves, meaning the macroscopic part cannot be reduced to its microscopic parts. It emerges from something else, something that we haven't been able to measure. So the question is, are consciousness and memory both emergent properties? And thus, could they be replicated without having to directly reverse engineer the neural processes of the human brain? Hopfield's aim was to answer this question, and he took inspiration from a natural principle that governs many physical systems: the tendency to evolve towards lower energy states. He developed an algorithm based on an energy function, with each memory corresponding to a stable energetic state. The goal of this algorithm is to drive the system's energy as low as possible. At that point, the neurons stop firing and the network will have converged to a stable pattern, hopefully a pattern associated with the input that caused the network to change, constituting a memory. The system would then function as content addressable memory, as opposed to random access memory or RAM found in computers, where each memory trace is linked to an address that maps directly to a node in a computer's central processing unit. So computer memory is more like a direct mapping than a dynamic system. So mathematically, Hopfield showed that the state of the system corresponds to a value of the energy function E. So minus half sum that. So the state of the system corresponds to a value of the energy function. The neurons are defined as V. These are binary because neurons in the brain are also binary. But in the way that he's computed it, he sets the neurons as -1 and +1 because it just helps with the algebra. The connection weight, W. In the paper it's T, but I just wrote W. So if you watch the last video on the perceptron, you'll see that the equation here is kind of similar. It's a weighted sum. You can kind of use it as an analogy for how the neurons in the brain works. The weights would define the connection between two neurons, how strong that connection is, and then the two V's would be the two neurons connected. So the sum would be the state of the network at a specific time. This, the minus, why is it there? It's not random. So as I said, he set the neurons to be -1 and +1. So they're not firing together. It's -1. They are firing together. It's always going to be a positive one. So you add the negative because what they discovered in physics is that most physical phenomena tries to reach a lower energy state, especially if there is the lowest energy state within a system. The whole system will try to move towards that low energy state. And when Hopfield referred to a lower energy state, he's not only talking about literal physical energy. He uses the term energy as an abstract measure of a system's stability. So physical systems tend to evolve towards stable states. You might be thinking, wait, but doesn't entropy tend to increase? There's a very complicated relationship between this phenomena and entropy, which has something to do with the free energy principle. And I hope one day I will be able to explain it. So what he tried to do here, by adding the minus, he's saying that when two neurons firing together, which creates a positive value, he wants to flip that and make it negative. Flipping it into a negative would make the co-activation be a lower energy state. So what he was trying to do is say that when a pattern emerges in the system, this corresponds to there being a lower energy state. So that's kind of what he was trying to encode into this system. So even though technically the weight can be on a continuous spectrum of values, the actual function is discrete because it only changes when each neuron changes, and each neuron can only change between -1 and +1. So the system can only change between discrete values, making it a discrete function. So the way he computed the change in the system or change in the energy of the system, this is literally a partial derivative of this function. So how did he get a derivative of a discrete function? You might be asking. I wouldn't be able to explain that to you guys because it is a discrete function, and I'm pretty sure you can only have a derivative of a continuous function. So yeah, I'm not going to go into an analysis of whether this is accurate or whether, like, you know, the limit exists. I mean, you can see here, like, okay, so if you think of these two v's as v squared, then the derivative of this with respect to, so if you take that over there, with the derivative of the energy function with respect to the neuron I, so that would become 2/2, so that would become 1, and this, so it would only be 1v, not 2v's, and then you'll get this, and you've kept the weight vector constant. Because, so yeah, it's literally a partial derivative, but it's a discrete function. So yeah, I can only guess that in the limit, this would probably be minus infinity. But yeah, eventually they ended up using continuous functions, so this kind of doesn't matter. But yeah, so theoretically, if you have this, if you know how the energy function changes, you can figure out, if you change one neuron in the function, you can figure out how the energy function would change. So the goal is to reduce the energy function as low to a lowest state as possible. So all you have to do is keep changing each neuron and keep redoing the calculations until you've got the energy state to a lower and lower state. So yeah, but then in an actual artificial neural network that is being trained, it would have to figure out also the weights. So how would you change the weights in order to also get the energy function to be as low as possible, which is basically corresponds to figuring out a pattern that corresponds to a memory. But here's the thing. We could ask if this algorithm or process diverges from the microscopic computations of the brain. For instance, does the brain calculate changes in its internal states as a linear function, even though its variables are discrete? Actually, are the brain's variables really discrete? What we know from the Hodgkin and Huxley experiments is that the evolution of neural signals could be modeled with continuous differential equations. So I can't really think of a reason why the brain wouldn't be able to utilize these signals. But it's definitely not linear. The dynamics are definitely more complicated. We could also ask, how would the flow of bioelectricity in a stochastic system compute an exact delta signal? Or we could ask a more fundamental question, one that we know from modern AI research is significant. At the time, and to be honest, even now, sometimes we don't have one definition of certain terms. People might interpret different things in different ways. I personally would describe a Hopfield network as a synchronous system, or at least a sequential asynchronous system, because the updates are made one at a time. There's not distributed computations being processed in parallel, kind of like what the brain does. But at this stage, the idea of asynchronous neural networks basically just meant that there was no set time to run each computation, like what you see in traditional computers. Everything was computed separately but at the same time, and then they were added together and processed. I mean, due to technological constraints at the time, I don't think they would have been able to do parallel processing, even if they thought of it, which they probably did. But they would have needed GPUs. So, yeah. So we had all these constraints, some that I probably haven't even thought of, that made these algorithms, or that made the Hopfield network far from a reverse engineering of the brain or reverse engineering of what we know to be intelligent. And yet, the success of Hopfield networks was seen in its emergent properties like generalization, categorization, and error correction, or things that were not encoded into the system. So something of the form of intelligence had emerged from a less complex information processing system, which forces us to ask, what is it about information that causes all these phenomena? Or maybe an easier question would be, what actually changed between the time of the perceptron and the time of Hopfield networks? The solution was time itself, or at least the concept of time.
We describe kind of the progression of computation turns out to be what we think of as time.
Film a car speeding down a road. Speed up the image infinitely, and the car disappears. So what proof do we have of its existence? Time gives legitimacy to its existence. Time is the only true unit of measure. It gives proof to the existence of matter. Without time, we don't exist.
So we spoke about perceptrons in episode 2, and I spoke about how perceptrons basically process input data to directly analyze features of the patterns themselves, features of the data itself. Hopfield networks use input data as a form of stimuli to perturb a system and analyze how it changed across time. So Hopfield networks didn't need to directly analyze input. They were a memory storage system that could be activated by stimuli. This idea reignited the field of artificial intelligence. Geoffrey Hinton later extended this research into Boltzmann machines, and together they won the 2024 Nobel Prize in Physics. And so, from the single-layer perceptron, deep learning emerged. The dawn of artificial intelligence had arrived. So at this point in history, most AI researchers thought that the theoretical foundations had been established. The most pressing issues, like distinguishing between nonlinear features, had been addressed. So now their goal was optimization. Deep learning became the star of the show. These techniques repurposed mathematics developed by Isaac Newton and mathematicians from centuries ago. An 1847 paper written by Augustin Louis Cauchy is literally where gradient descent originated. It's kind of like what we discussed with the Hopfield networks, derivatives and error functions. It's a way for AI to learn a configuration for the connection weight. Further optimizations refined these algorithms into something far more capable: the convolutional neural network. Deep learning's defining breakthrough. By the late 90s into the 2010s, convolutional neural networks accumulated evidence, experiment by experiment, that computer vision was entering a new era. This algorithm took inspiration from the hierarchical structure of the human visual cortex. In the brain, the visual cortex is organized in layers, where each layer consists of neurons that focus on a specific visual field or specializes in a specific aspect of perception. So one layer might process textures, while another might process edges or shapes. At higher layers, these individual computations are integrated to generate perception. The use of this architecture originated with Kunihiko Fukushima's neocognitron, and then Yann LeCun applied backpropagation, which exploded the intelligence of convolutional neural networks. You can intuitively understand why this architecture is so powerful. Imagine having these images. If you process everything at once, you'd find it really difficult to differentiate between the two. But if you process individual pieces, you get more nuanced information. It's the same type of universal principle we spoke about in part 2, of taking advantage of higher degrees of freedom by integrating computations from smaller units to generate complexity. The power of convolution, especially in the brain, came from its ability to detect new features for different objects and to detect features we aren't even aware of. So research has found that the visual cortex in the brain not only encodes more abstract patterns than what is encoded in artificial neural networks, but they can also be context dependent. So the patterns encoded are unique. Artificial neural networks seem to only encode simple features like shape or texture. This means there's some mechanism in the brain that allows the visual cortex to encode more nuanced and complex patterns. So all of this points to the fact that, at least at this stage, AI was largely pattern recognition instead of intelligence. It couldn't encode features beyond what made logical sense. So if I was to rename artificial intelligence, I would call it advanced information processing, because what it does seems to be more logical, and there seems to be something about intelligence that is beyond logic, at least the information processing that leads to intelligence. But I did see in a podcast that Sam Altman wanted to describe artificial intelligence more as alien intelligence. But yeah, I think just using the word intelligence would be a bit misleading. What do you guys think? How would you define intelligence or artificial intelligence? So, although convolutional neural networks were a lot more powerful than what they had before, and maybe reverse engineering the exact microscopic details of the brain isn't necessary, but we still hadn't been able to reverse engineer the power of the visual cortex or the brain, if we're assuming that the microscopic details of the brain is separate from its power. Deep neural networks were actually quite powerful and had a lot of potential. An analysis of the universal approximation theorem proved how intelligent deep neural networks were by proving that neural networks could approximate any continuous function. This tells us that you can use neural networks to represent almost any dataset that represents phenomena that acts within the laws of nature, or at least where you can approximate things to act within the laws of nature, since we're using derivatives and gradient descent, so the functions that are approximated need to be continuous. The problem is, just because you can approximate these functions doesn't always mean you can solve their resulting error function to a high accuracy. Convolutional neural networks are an example of what I've been talking about throughout this series. An example of how we fail to build intelligent systems that are more powerful than humans, or even just on the same level of intelligence as a human. Convolution is an idea inspired by the intelligence of the brain, and so is separate computational units like neurons. But the way artificial systems learn and process information is through backpropagation, gradient descent, differentiation, ratios, multiplication. Many scientists have argued that the brain just cannot implement backpropagation for reasons that basically stem from its nature as a biological living system. So, for example, the weight symmetry problem. How neurons in the brain most likely don't have a mechanism for perfectly copying connection weights recurrently. They also likely don't have mechanisms for implementing continuous numbers or continuous functions, and activity in the brain is truly asynchronous. I think the most profound point is that the brain operates on about 20 watts of bioelectricity. Backpropagation requires extremely high precision computation and global coordination that would be metabolically unrealistic for biological tissue. It's actually been proven that it's impossible to directly reverse engineer the computation of the human brain, which potentially means that AGI is impossible, at least an AGI that directly reverse engineers the brain. So what I've been talking about throughout this series is we need to come up with algorithms that are more efficient than God and nature have created. So this brings us back to the question, what is complexity? It's possible that backpropagation and many other mathematical or logical systems just limit these algorithms. It's a computational limit meant to allow these computers to process information and data, because it's kind of the only way that they can do that. Like, that's kind of how they're designed as logical systems, not living systems, or at least not biological systems. In the next episode, which is also the last episode in this documentary series, I'm going to show you evidence of exactly how backpropagation can limit an intelligent system.